Sorun yok. O zaman insertion sort ile devam edeceğiz. Okay. Let's continue with the next sorting method, which is called insertion sort. Again, in insertion sort, we have an array of elements, and we try to insert each element one by one into a sorted sequence. So, for example, we can copy this first element here, and it is sorted, right? Then we can insert second element into this sorted sequence and make the first two elements to be sorted, and insert third element in the sorted sequence, etc. Actually, we do not need to use extra arrays in here. We can sort in place. So first we assume that this part of the array is sorted. The first element is always sorted, right? And we insert the second element in the sorted array. And then after insertion of second element in its correct position, first two elements will be sorted. And we insert third element in this sorted array. After inserting third element in the correct position, first three elements will be sorted. After inserting several elements, all these elements are sorted, and we insert the next element in the sorted sequence. So at last, we have sorted everything until the last element, and after inserting the last element in this sorted sequence, the whole array will be sorted. Okay, but how are we gonna insert this element in the sorted sequence? These are sorted, and we have to insert this element. How we are gonna do it? Simple. We are gonna copy this element in somewhere else, and as long as the element here onward to the left are larger than the element that we have put aside, the elements are moved to the right. And at the end, we make sure that the elements here are larger than the element that we put aside, and elements here are smaller than the element here. So we put it in its correct position. Okay, this is the algorithm. The insertion algorithm is quadratic sort algorithm again. It is similar to how card players arrange their hands. So we keep a sorted list of cards, and after picking another card, we put in its place, for example, 8 in this case, and 7 in this case, etc. So we insert a new card into the hand is performed one card at a time. So when a player picks a new card, makes a room for the new card and inserts it in its proper position. Okay. So this is the algorithm. For array elements from second to last, why we didn't consider the first one? First one is always sorted by itself. So this part is sorted. So we do not need to consider the first element. Okay, we insert the element where it belongs in the array. Okay, and we continue like this. So first we insert 25, then 15, then 20, and then 28, and we will end up with 30 seconds. Okay. After first 2 iterations, the array until here will be sorted, and we insert 20 in this sorted sequence. Okay, this is the simple algorithm. Of course, this second step has to be detailed. This is the refined version. The second step is written in detail. So we have the next position will be from second to last, from 1 to n minus 1 actually. So we will insert the element in this position. So first we insert this one, then this one, then this one, etc. First we save this element, save the value of that element in next value. So we put aside 25 at the first iteration. And in this while loop, while position is greater than 0, and the element at next position minus 1 is greater than the next value, we shift this element in next position. And decrement next position, of course. Next position will be from current value and decremented by 1 each time until 0. So this while loop will terminate if we get to the end of the array, or we find a smaller element smaller than next value. In that case, there's a place opened up, and next position, next value, the element that we put aside will be saved in that position. So let's see the trace. Okay, so a loop position is at the first position. So the loop iterator of this for loop is this one, loop position, and that is saved to next pos, and 25 will be saved aside in next value here, as you see. And while next pos is greater than 0, next pos is 1 right now, and greater than 0, and the previous element 30 is greater than next value 25. So we continue with the iterations of the while loop. So we take this 30 and move one position the right, copy this element in this position. So we put 30 in place of 25. 25 is lost, but it is saved here, so it is not lost actually. It is lost in the array, but it is put aside, saved in somewhere else. We decrement next pose. Since next pose is not greater than 0, so we get to the end of the array, we get out of the loop, and we put this 25 in its place, next pose. Okay. After this operation, first iteration of this outer for loop is finished, and we are sure that the values here are sorted. 25, 30 is sorted. In the next iteration of the for loop, we are going to insert this 15 in this sorted array, right? So next pose points to 15, and this value 15 is put aside here. And in the while loop, since next pose is greater than 0 and this 30 is greater than 15, we perform shift operation and decrement next pose. Next pose is still greater than 0, and still this 25 is larger than 15. So we will perform one more shift operation and decrement next pose. Right now, next pose is 0, so we get out of the loop because of this condition. It should be greater than 0, but it's not right now. So we get out of the loop and copy this 15 in its place, as you see. After this operations, the elements here are sorted, 15, 25, 30. And during third iteration, we are going to insert 20 into this sorted sequence. Again, next pose is initialized, and next while is initialized to be 20. This value is copied. And in this while loop, we compare 30 with 20. 30 is larger, so it should be shifted. And 25 is larger, so it should be shifted. But 15 is smaller than 20. So we get out of this loop because of this condition. And after we get out of the loop, we copy this 20 in its position. Now all these values are sorted. Okay, at the last iteration, we insert 28 into this sorted sequence. Next pose is initialized, and next value is set by 28. 30 is larger, so in this while loop, we have to shift 31 position to the one position down, and decrement next pose. And when we get to this while loop condition again, 25 is smaller than 28, this condition is not satisfied. This condition is okay, but this condition is not. So we get out of the while loop, and this 28 will be inserted in this position. So we open up a position for next value, and here we open up a position for the next value in its correct position and insert the next value in its correct position afterwards. So after this, the whole array is sorted. Okay, this is an insertion sort. You all probably know the insertion sort. Now we are gonna perform this analysis based on comparison and exchange. Which comparison we are talking about? We are talking about this comparison, right? Comparing these two elements in the array. And exchange is this shift operation, right? So we move the elements in the array. Okay. How many times this comparison and exchange are performed? It depends on the array, right? The elements in the array. Not only the number of elements. It doesn't depend not only the number of elements, but also the values in the array, right? So we have to talk about best and worst case. Since the number of comparisons and number of exchange depend on the values in the array. Okay. In the best case, this while loop exits because of this, and at the before the first iteration of the while loop. So the while loop inside of the while loop is not executed at all. So this condition is not satisfied when we get to the while loop at the first time. And this happens if the array elements are sorted as in here. We give these elements to be sorted by insertion sort. Then we are inserting 20 into this sorted sequence. 20 is larger than 15, so this is not executed at all. Or when we insert 28 into this sequence, 28 is larger than 25, so these are not executed at all. So, as far as the comparisons are concerned, only one comparison is performed for each iteration of the for loop, and n-1 iterations are performed in overall algorithm. So the best case number of comparisons is n-1. What about number of exchanges? As you see, there is no exchange performed. So in the best case, number of exchanges will be 0 in the best case. In the worst case, the while loop is terminated because of this condition. This condition happens when the value here is inserted in this sorted array, and all the whole array elements has to be shifted, right? And the element put aside should be inserted in this position. That is the case if all these elements are larger than the currently inserted element. This is not the case in this example, but you can see if this element is smaller than all these elements, then we have to shift one position to the right, all the elements, right? So this condition has to be checked for all these elements. If we are at the kth iteration, there are k minus 1 elements here, right? So the first iteration, we have one element. In the second iteration, we have two elements. In the nth iteration, we have n minus 1 elements. So the number of comparisons is the addition of these elements, right? These numbers. So n times n minus 1 over 2 comparisons are performed. After each comparison, we have to perform a shift operation. So n minus 1 over 2 exchanges has to be performed as well. As you see, this is the first condition in the while loop. And since it is not satisfied, the second condition is not checked. And if you check it out, it will give an error since there is no element in next pose minus 1 is net. If the next pose is 0, there is no minus first element in the array. So number of times this condition is evaluated and number of shift operations are same. Usually number of condition evaluations are one more than the number of times the inside of the while loop is executed, right? But in this case, they are same since the while loop terminates because of this first condition. Okay, so as you see, number of comparisons in the best case is theta n. In worst case, theta n squared. Number of exchanges theta 1. And in the worst case, it's theta n squared. And the running time of the algorithm is theta n squared. So it is quadratic time algorithm. Right? So insertion is performed n minus 1 times. And number of comparisons and number of exchanges during each insertion depends on the values. Not only depends on the number of elements in the sorted array, sorted subarray. In the worst case, all the elements in the sorted subarray has to be compared with the next value. So the maximum number of comparisons will be the sum of these values, which is theta n squared. Best case of insertion sort is when the array is already sorted. At each iteration, at each insertion, we have to perform only one comparisons. So in best case number of comparisons is T10. In this case, no shift is performed, no exchange is performed. And actually, when you look at this algorithm, you perform a shift operation. So a value is copied in another value. But in, for example, bubble sort, we have to exchange two values, yeah, right? We compare two elements, consecutive two elements, and exchange it. To be able to exchange it, we perform three copies, actually. Not one, not two. We have to copy one of them into a side and copy second one into here and here. There are three copy operations are performed. But in insertion sort, only one copy operation is performed. So that's why a number of, although the number of exchanges in the worst case n squared for both bubble sort, insertion sort, and selection sort, since only one copying is performed for each exchange in insertion sort, even in the worst case, the insertion sort algorithm performs better. So the shift in insertion sort requires one data movement, while exchanges in bubble sort and selection sort involves three items to be moved, right? Of course, these move operations are, if the elements are primitive type, elements are moved. But if they are object type, the reference of the objects are moved, right? Of course, we do not change the location of the objects, but their references are moved. So the performance of the insertion sort is better in that sense. And when you look at the number of shift operations performed during an insertion, it is one less the number of comparisons. But if the value is smallest, number of comparisons and number of shift operations are same. It means that if the worst case happens, number of comparisons and number of shifts are same. Okay, we have said that before. And this is the code for the insertion sort. As you see, we have a sort algorithm which uses insert method here as a helper method. Okay. In a insert sort method, we go from first position to the last position, insert the element at that position into sorted sequence in the table until that position, right? And it's performed by using this insert method. So insert method inserts the element at next pose into where it belongs in the array. It assumes that the elements until next pose are sorted. And at the end of the operation, the elements, including the next pose, will be sorted. Okay? So, because of that, at the beginning, the first element is sorted. That's checked, right? And after the first, in the first iteration, this one is satisfied since the first element is sorted. After the first iteration, these elements are sorted, right? And before kth iteration, the elements here, the k elements here are sorted. And index k element will be inserted. After the kth iteration, this k plus 1 elements will be sorted, right? Because of this, after n minus 1 passes and n minus 1 iterations of this insert operation, the whole array will be sorted, right? So loop invariant says that for kth iteration, the elements from 0 to k minus 1 is sorted, and the element at k position will be inserted in this sorted sequence. And the whole first k first k plus 1 elements will be sorted after the insert operation. Okay? Any questions? This insert is performed here. As you see, first we save the element at next pose in a temporary position. Then while next pose is greater than 0 and the previous element in that position is greater than the next value saved, put aside, we shift and decrement next pose, right? Simple implementation of the algorithm. At the end of this while loop, space is opened for the next value and it is copied over there. So this is the end of discussion about insertion sort. We can compare all these quadratic sort algorithms as in here. You should consider all these to be theta instead of big O, right? As far as the number of comparisons are concerned, as you see, selection sort is always theta n squared, but bubble sort and insertion sort can be linear number of comparisons in the best case.
Sir, you said instead of O notation, we should use theta notation. Why was the reason behind that again?
We have said that, right? As you see here, we have used theta notation. You can assume all these are theta. We have used that, right? Here, you see, right? We have used theta notation.
Yeah, I do get But why shouldn't we use, then I should put it this way, why shouldn't we use O notation?
O notation is correct as well, but not complete. You all know
Okay.
what is the difference between O n squared and theta n squared, right?
All right, I see.
O n squared is correct for selection sort's best case, but better to use theta n squared, saying that n squared operations are gonna be performed. But if you say O n squared, it can be n plus 5 as well, right?
Correct.
That's why it's better to use theta notation instead of big O notation in here. Okay? And when you look at this table, you can see that for as far as the number of comparisons are performed, bubble sort and insertion sort performs better than selection sort. And if you look at consider the exchange operations, since best and worst case performance of selection sort is linear, as far as the exchanges are performed, selection sort seems to be better, since worst case is linear as well. And when you compare these two algorithms, insertion sort and bubble sort, as you see, both are worst case and squared, but for bubble sort, the best case is constant. There is no exchanges performed. Actually, this is linear. I made a mistake over here. It is linear since the number of shifts here is 0, but there is a comparison here. No, there is a copying here and here, right? There are two more copies, not in the while loop, but out of the while loop. Two copy operations, copying of this value to be inserted over here and back in the array, okay? Two copy operations are performed. And because of that, even in the while loop, there are 0 copying are performed, but still 2n-1 copies are performed. That's why this is linear because of these two copy operations, right? That's why this value is linear and it's correct. Okay. When you look at these quadratic running times, while n increases compared to n log n values, n squared grows a lot faster than n log n. For small values, difference is tolerable, but for large values, n squared is a lot larger than n log n. So these quadratic running times are too big. Too long time is required to sort compared to n log n. There are n log n sorting algorithms that we are going to see. When you look at these three algorithms, experimentally, compare the running time, Tn, insertion sort performs best So insertion sort gives the best performance for most arrays. Because it performs just shifts instead of exchange. And it keeps a partial sorted array. Also, bubble sort usually gives the worst performance. But we don't see this case here. As long as the worst case performance are concerned, they are all same in terms of the comparisons. But as you remember, there are some constants hidden here, or constants hidden here, or actually not in number of comparisons or number of exchanges. We can talk about running time. All of them are theta n squared, right? But there are constants hidden here, right? That we ignored in this theta notation. In the worst case, of course, these are worst case performance, right? Worst case running times. And we can say that the constant for the bubble sort is larger than constant of insertion sort. That's why the insertion sort's running time is usually better than running time of the bubble sort. And these quadratic running time algorithms are not useful for large arrays since the running time depends on this value, although the n log n running time algorithms are a lot faster, depends on this value. So quadratic time algorithms are sort algorithms are not good for arrays, larger arrays. Try to use n log n algorithms like merge sort or quick sort instead of these quadratic sort algorithms. But their best case performance, especially for insertion sort, best case performance is a lot better than n log n algorithms. That's why you can prefer these algorithms if the array is almost sorted. So where is it? Doesn't say here. If the array is almost sorted, you can prefer quadratic sorting algorithms over n log n algorithms like merge sort or quick sort. Okay. In some quadratic sort algorithms require extra array as well, extra storage as well, besides the array that we use as input. Extra memory space is used, some of these n log n algorithms, but in quadratic sort algorithms, there is no extra storage is used, and extra storage use is constant. So we sort the array in place. We do not use extra array to perform our sort operation. But in some n log n algorithms, for example, merge sort, we will use extra arrays. That is a disadvantage of merge sort. So the extra space used for these quadratic sorts are constant. Of course, we use comparator method, as you see here. Comparator method is used to compare elements. Of course, you can use comparator instead of these comparator methods. And the running time of the algorithm depends on the complexity of comparator as well. When you compare these two operations, comparison and exchange usually moving the references, but comparison requires to call this comparator method. A method call is used. So comparison is usually more time consuming than exchange operations in Java. For some other languages, exchange may require to move the elements itself, move the information rather than references.
Sir,
Yes.
Can we leave, by the way, other lessons have started for us?
I didn't get it. Repeat again.
Can we leave because other lessons have started for us?
Oh yeah, it's we have. Okay, we will start continue with the shell sorts. Yes, you can leave it, of course. You can leave, and we will
Thank
start.
you, sir. Have a nice day.
You too. We will continue with shell sort in next session. The only thing that I should say here, in some other languages, the exchange operation requires moving the information. In that case, exchange may take longer than comparison. Exchange may more costly than the comparison in some other languages, but in Java, comparison is more costlier. So when we compare these algorithms, we can consider these comparisons more than exchange in Java. Okay. Next time we are going to continue with the shell sort, as I said. So let's stop here. Okay. See you next time.